In this section, we're going to dive into a very specific type of sequence, which is called an arithmetic sequence. First, we're going to learn how to determine whether or not a sequence satisfies the properties of being arithmetic. Then we're going to find a particular term in the sequence. And then finally, we're going to find the sum of an arithmetic sequence. And remember, that's what a series is, right? A series is what you get when you add up all the terms of a sequence. So fundamentally, an arithmetic sequence will go from one term to the next by always adding or subtracting the same value. That number that we're going to be adding each time is going to be called the common difference. And in our formulas, we are going to notate that common difference using the letter D. Arithmetic sequence can be defined recursively as setting our first term equal to some number, maybe we'll call it A, and then each additional term in the sequence, so as a general description, A sub n, how we get to that nth term is we take the previous term, the one right before it, so in using the subscript notation, that's where you're going to get the A sub n minus 1, and then you're going to add to it that common difference. So to get to each successive term, you're going to take the previous term and add that number. We call this number D the common difference because when we're looking at a sequence, that's what we're going to do in order to find that value. We are going to take the difference or subtract successive terms, and we're going to see then if we do that subtraction, do we always get a constant value? So maybe there's another way to write it then, that common difference D, if I just take this and solve for D, how I can find D is I can do an minus 1. So just subtract two successive terms. So let's take a look at a couple of examples, and we're going to show that the sequence is arithmetic. Right? So we're going to be kind of given that each one of these is arithmetic, and we're going to verify it is. We're going to list the first term, and then we're going to also find the common difference. So for my first sequence, it's 4, 2, 0, negative 2, and so on. Right, so my first term can be notated as A sub 1, and in this case, it's going to be 4. Now, the next step is to find that common difference. We're going to subtract successive terms. And when you do the subtraction, it's always going to be in the order of further in the sequence minus its previous term. So for these first two terms, I would do 2 minus 4. When I do that, I get negative 2. If I had grabbed the next two terms, we would get 0 minus 2, which is also negative 2. If I had grabbed the next two terms, I would get negative 2 minus 0, which is also negative 2. So we're seeing here then that it doesn't matter which pair of successive terms that I grab and I subtract, I'm always getting that set number. So for this problem then, my common difference, which I can use D to represent that, is going to be negative 2. So in this case then, the thing that I'm doing to get from one term to the next is I'm subtracting that set number, but when we talk about the common difference, we always talk about in terms of like an adding relationship. So that's why we refer to this as the common difference as being negative 2, because that's what I'm adding every time. So maybe as another way of phrasing that, if you are subtracting a set number every time, your common difference will be negative. Right? That's how we're going to handle the subtraction. All right, let's take a look at our next example. So for the next example, we're given the sequence using an explicit formula. So S sub n, that sequence, is going to be generated by the expression 4n minus 1. All right, so to find the first term, maybe let's do that first. So s sub 1, the first term, is going to be found by doing 4 times 1 minus 1. Okay, so 4 minus 1 is 3. So my first term is 3. Now, to find that common difference, then, you could find the second term. You could find the second term, s sub 2, figure out what that number is, and then subtract these values over here. That will tell us the common difference, but for this problem, because we are given the formula, we want to find this true. That's going to be true in general. So in general, what I need to do to find my common difference, okay, so let me write in a little note here, so when we look at our work later, we can figure out what we were trying to do here. The common difference in general is going to be found by doing s sub n minus s sub n minus 1. Right? Take a term and subtract the previous term. And we're going to show that this is going to hold true for any value that we put in for n, basically anywhere we are in the sequence. So s sub n is given to us by 4n minus 1. I'm going to subtract from that s sub n minus 1. So in this notation, what this means is in my general explicit formula, everywhere I see an n, I'm going to write n minus 1 instead. So because I'm going to be subtracting off a bunch of stuff, don't forget about the set of parentheses right here. So I'm going to have 4 and then another set of parentheses, n minus 1 is the subscript I want to use, and then minus 1. Close the parentheses. All right, so I have a little bit of distribution that I need to do here. So just inside this set of parentheses, I'll have 4n minus 4 minus 1. All right, so I want to subtract all of that stuff. So I'll get minus 4n plus 4 plus 1. And we're going to get a bunch of canceling that's going to happen here. So this 4n will cancel with that minus 4n. This minus 1 will cancel with this plus 1. And when everything's said and done, the only thing I have left is that 4. So that is going to be my common difference, D. So again, I could have found s sub 2 and subtracted it, but for these types of problems, when we ask you to find the common difference, we are looking for you to justify it in more general terms. Because I'm given the formula, it's not enough just to find that it holds true over a couple of terms. We can actually verify algebraically that it will hold true in general. So let's take another example of doing this with a formula just to kind of clarify what it would be to find that common difference. So for my next sequence, it's t sub n is equal to 2 minus 3n. Right? That's the explicit formula. So maybe you take a moment and find for me then the first term and then find for me the common difference. So go ahead and pause this, try that on your own, and then let's check it against what I'm about to write and see if you're on the right track about verifying that sequences are arithmetic. Alright, so let's go ahead and solve this and see if this matches what you got. So for my first term, t sub 1 is going to be found by doing 2 minus 3 times 1, which is 2 minus 3, or negative 1. So there's the first term in my sequence. To find my common difference D, I'm going to do t sub n minus t sub n minus 1. So t sub n is 2 minus 3n minus, so now I need to find t sub n minus 1, so it'll be 2 minus 3, and where I see the n, I'm going to substitute in an n minus 1 subscript instead. Alright, so let's go ahead and clean that up. So that'll be 2 minus 3n in the front, and then minus, just cleaning up what's inside the parentheses, I'll have 2 minus 3n plus 3. Now you could combine like terms in here, but you're going to find that you're always going to get a lot of nice canceling because this has to be arithmetic, mainly because we are told in the directions, but when you verify that something's arithmetic, you're going to find that pretty much everything is going to cancel except for whatever that common difference is. So I have this positive 2 and negative 2 that can cancel, this negative 3n and positive 3n that can cancel. When everything's said and done, my common difference is going to be negative 3. Now, you might have been noticing a little bit of a pattern that's happening in those formulas when we give you the sequence explicitly. So let's make a connection to something that we've seen previously. When you have a linear function, that will have the general structure of y is equal to mx plus b, right? Where inside that function m is your slope. And your slope can be thought of as your constant rate of change. Right? It's how fast your y is changing with a specific change in x. Well, that's exactly what our common difference is. Our common difference is that the output or the terms in the sequence change at a very specific rate with a specific jump in x. So probably the easiest way to do it is to think about if x changes by 1, or you go from one term to the next, how much is y changing? That's going to be your common difference. This idea can help us find a formula for an arithmetic sequence, which is going to be a general formula for any nth term in the sequence. So let's start off by finding out where this formula comes from by writing out a few terms. So the first term in your sequence, you can denote it as a sub 1, or sometimes it's just written as a. I'm going to leave it as a sub 1 just to be very clear that I'm looking at specifically the first term in the sequence. But just the same way that if I have, for instance, x, we know that the 1 is implied there. Moving forward in sequences, sometimes we stop writing the 1 after that because we assume that the first term is going to just be a. I like to write the 1 there because we're just learning this, and the position, that number in the sequence, is very important. So I just like to put it there to remind myself I'm looking at the first term. Okay, anyway, a sub 2 is equal to, recursively, I take the previous term, a sub 1, and I add my common difference, d. Okay, that's not too bad. The next term in my sequence, a sub 3, is equal to a sub 2, the previous term in my sequence, and I'm going to add that common difference, d. But a sub 2 is equivalent to the expression a sub 1 plus d. So if I substitute that in, a sub 1 plus d, that's substituted in for a plus 2, then I'll have this other plus d, so then I get a sub 1 plus 2d. A sub 4 is equal to a sub 3, the previous term, plus my common difference d. But a sub 3 is equivalent to what I have written above, which in its most simplified form was a sub 1 plus 2d. So if I substitute that in, I'll get a sub 1 plus 2d. That's what a sub 3 is. Add another d. These are like terms, I can put them together, so I get a sub 1 plus 3d. Alright, so hopefully we see enough of the pattern here that we can just stem this out. When we're going to find a formula for an arithmetic sequence, what we're going to do is we're going to find a general expression for the nth term. Alright, that's what our goal here is. So the nth term can be found by, well, let's take a look at what we found here. A sub 3 ultimately had started with a sub 1, and then I added 2d to that. If I look at a sub 4, it started with a sub 1 and I added 3d to that. So for the nth term, it's always going to start, I can always go back to whatever that first term is, my a sub 1, but I will add to it a certain quantity of my common difference d. Now, how many for the d will I be adding to it? All right, so I know I'm going to have a d in here, so let me put it down. How many will I have? Well, for the second term, I only added 1 value for d. For the third term, I added 2 of my common difference, because I was 2 steps away from my first term. For my fourth term, I added 3 of my common difference, because I was 3 steps away from my first term. So in general, for the nth term, I will need to add n minus 1 of my common difference d in order to get out to that specific term in my sequence. All right, and now we normally would leave it like that. We don't distribute the D through or anything like that because the value for A1 and D and then N being a specific position we are in the sequence are all very important. What I have seen some students do though is rearrange the terms. So they've written this as A1 plus D N minus 1 or D N minus 1 plus A sub 1. So in the reasons for rewriting it, one is for the parentheses expression. I think a lot of students are just comfortable seeing that multiplier in the front, so it bothers them that it's on the tail end. The other thing that these structures, though, are starting to mimic is what's going on up here with this linear function. This would be your mx and then plus b. So you can see kind of like your y-intercept is going to be that starting value, and then your common difference is mimicking what's happening with your slope, that constant rate of change. Okay, so however that's going to help you remember this, because this is something that you will need to have memorized. Okay, that helps commit it to memory, but the formula then tells me that for any specific term in my sequence, okay, we're going to need one less than that, and then multiply that by the common difference, and then we're going to add that to the first term. That's going to tell me basically how many times I had to add that common difference to the first term to get to that specific term in my sequence. Alright, so then all we're going to do is just kind of record that in general. So for an arithmetic sequence A sub n, whose first term is A, now as a reminder, A can be thought about being the same thing as A sub 1. Right? Sometimes we suppress writing that subscript for 1, but they mean the same thing. And whose common difference is D, the nth term is determined by the formula A sub n is equal to A sub 1 plus n minus 1 times D. And the cool thing about this formula is if you forget it, it's really easy to recover. If you just write out a couple of terms in your sequence like we did up here, you can start seeing that pattern pop out, which can then get you back to that general formula. Let's use this formula on a couple of examples. So for our next example, we're going to find the 24th term of the sequence -3, 0, 3, 6, and so on. Okay, so we are told it's an arithmetic sequence, so this will have a common difference. So if I just want to grab any two terms, and it doesn't matter which two terms I grab, so it could be the first two terms, or it could be further out in the sequence if you prefer. If you subtract the terms, so I'm just going to grab the 3 and then the next term is the 6. So when I do my subtraction, I'll do 6 minus 3. So I'm getting 3 as being my common difference D. And my first term is -3. Okay, so the general formula is A sub n is equal to A1 plus n minus 1 times D. In this problem, though, I am given that I want to find the 24th term. So for this problem, my value for n is 24. Putting that into my general formula then, what this is telling me is that if I want to find A sub 24, that is going to be equal to the first term, which is -3, plus 24 minus 1 times my common difference, which for this problem is 3. Alright, so if I just want to clean this up, I'll get -3 plus 23 times 3. Alright, so that's going to get me -3 plus 69, and if I add those two values together, I get 66. Alright, so the 24th term in the sequence is 66. You definitely don't want to sit here and go out to the 24th term. Yeah, I've seen some students do that, especially when they forget the formula. Just know then if I, for instance, give you find the 233rd term of the sequence. All right, now this is starting to get a little silly to sit there with your calculator and then, add that common difference that many times to get that far out in the sequence. So it's important that you know how to use the formula. Now, just to show you a variation of this before we move on, this one I was given a very specific value for n, how far out I wanted to go in the sequence. but we could also just ask you to find the nth term of the sequence. And in that case, what we would do is the nth term, a sub n, is equal to a sub 1 plus n minus 1 times d, right? That's not going to change. My a sub 1, my first term, is negative 3 plus, I'm going to leave the variable n in there alone because I'm talking about this in terms of a generic value in the sequence, and my common difference was 3. Okay, so for this one then we would normally clean this up. So I'll be left with negative 3 plus 3n minus 3, or 3n minus 6. So this would be then my formula for a general nth term. I can use this formula to find that 24th term if I wanted, right? So this would just be kind of another way to answer this question. So if I had found this first, I can use this then. I would do 3 times 24 minus 6, which is 72 minus 6. I still get that the 24th term of the sequence is 66, right? Just a slightly different way of getting there. Okay, fun, fun, fun. Let's take a look at our next example. This one's going to be a little bit different. This one is going to say the 6th term of an arithmetic sequence is 26 and the 19th term is 78. So given that information, we're going to find the first term of the sequence and the common difference. We're going to give a recursive formula for the sequence, and then we're going to be asked in general what's that nth term of the sequence. What would that formula or that expression look like? There's going to be a couple different ways to solve this. So let me show you a couple different ways. First off, I'm going to write off what I'm given. So a sub 6, the 6th term of the sequence is 26. And then a sub 19 is equal to 78. So if we remember in general that a sub n is equal to a sub 1 plus n minus 1 times d. What we have then is from the first piece of information that we're going to be given 26 is equal to a sub 1, which I don't know, plus, now n is the position that we were in the sequence. So right now I'm dealing with the 6th position, so I'll have 6 minus 1, and then times that common difference that I don't know, so d. Right, so maybe just cleaning up that part, I'll get a sub 1 plus 5d. Right, so I get that equation. For my second piece of information, the output was 78. That's what I get for that term. The first term, a sub 1, I don't know, so 78 is equal to a sub 1 plus, and then my position was 19, so I'll have 19 minus 1 times d, which would be then a1 plus 18d. Pulling those two pieces of information to the side, we would get 26 is equal to a sub 1 plus 5d, and then 78 is equal to a sub 1 plus 18d. Now what does that look like to you? Right, I have two unknowns split between two equations. This is a system of equations. So very cool. We just don't see systems enough, and I really love systems. So you can solve this using systems of equations. The two major solution methods would be solving it by the substitution method or the elimination method. I think this one is perfectly set up for the elimination method. So I'm going to multiply one of these through, let's see, I'm just going to pick the second one. I'll multiply this one through by -1. If you need some review on how to work with systems of equations, let me know. I can give you some resources. All right, so I'm going to leave the first equation alone, but my second equation, I'm going to multiply it through by -1. So I'll get negative 78 is equal to negative a1 minus 18d. All right, and the reason why I want to do that is now if I add in my columns going down, I'll get negative 52 is equal to, and this is why I wanted to do that, is that the a sub 1s are going to cancel, and then I will end up with, over here, what is it, negative 13d? divide both sides by -13, I get d is equal to 4. All right, so I had two variables in my system, a sub 1 and d. I have now found my value for d. We can back substitute, which I usually just abbreviate that as saying back sub. I can back substitute then into any of the previous equations to figure out the value for the other variable. So I'm just going to use the first equation in my system, which is the 26 is equal to a1 plus 5d. All right, and all I'm going to do here is I'm going to substitute in the value for d that I just found, which is 4. So I get 26 is equal to a1 plus 20. Subtract 20 from both sides, we get 6 is equal to a sub 1. All right, very cool. We just solved our system. So let's see what I was asked to find. So first off, it says find the first term and the common difference. Right, so we have that. The first term is right here. A sub 1 is equal to 6. We found our common difference. We found that d was equal to 4. What else do we have to do? Give a recursive formula for the sequence. All right, so for the recursive formula, let's go ahead and write this over here. We assign a value to the first term or first few terms, but in this case I only really need to assign a value to the first term, and then I have to tell you then from that first term how to get to every term after it. So for this one, my first term is 6, and then we would say, okay, you want to get to any nth term, you take the previous term, which would be a sub n minus 1, and you add 4. You add your common difference. And that's it, because that by definition of what an arithmetic sequence is. The arithmetic sequence is you're going to have a starting point, your first term, then to get to every term after that, you add your common difference. All right, so there's my recursive formula, and then the last thing they asked me to do is find the nth term of the sequence. Okay, so for the nth term, my formula is a sub n is equal to a1 plus n minus 1 times d. So we're just going to talk about this in general then. So my first term was 6 plus n minus 1 times, and then my common difference was 4. All right, and in this case we're going to go ahead and clean this up. So I'll have 6 plus 4n minus 4, which will then give me 4n plus 2. So there's my general formula for any nth term in the sequence. All right, so I think I've answered everything that they've asked of me. All right, I want to show you one other way to solve this problem. You're going to be like, why didn't I start with this? Because once I show it to you, you're going to be like, this is much simpler. One of it is because there are sometimes a lot of different ways of thinking about these types of problems and these expressions, and there's no right or wrong way. And also, I'll be honest, I really just wanted to highlight setting up a system of equations because I just think they're cool. But here's another way to think about what's going on in this question. All right, so I was given that a sub 6 is equal to 26, and a sub 19 is equal to 78. All right, so I said you could think about that common difference as like a slope, right? So I can think about the common difference as being that constant change in my output, which is a sub n, over a constant change in my input, which is the value for n, the position of where I am in the sequence. So for this problem then, my change in my output, which would be 78 minus 26, that's 52. Over my change in my input, which would be 19 minus 6, or 13. And then if you just simplify this ratio, 52 over 13 equals 4. So there's your common difference. Okay, so they also asked me to find the first term. Right now I just have the common difference, but if we use our general formula right here, so if a sub n, I'm going to move this over real quick to give myself a little bit more room. Probably should have planned that out a little bit better, but that's the nice thing is I can just slide things over. All right, so I have my common difference. If I now know that a sub n is equal to a1 plus n minus 1 times d, I'm just going to use some of the information I'm given. I'll just use the first piece because whatever, it doesn't matter. The output is 26. A1, I don't know, but I know 26 is the 6th term of my sequence, so I'll plug in my value for n being 6, and I know my common difference. Okay, so that's an equation that just involves one unknown, so I'm not going to take the time to clean that up, but if you clean this up and then solve for a sub 1, you'll get the same thing that we found, which is it's going to be 6. All right, so just a slightly different way of answering that question. All right, so the last little bit that we're going to look at in this section is how to sum a certain number of terms in our arithmetic sequence. And as a reminder, when you sum a bunch of terms in a sequence, that is what is referred to as a series. So if a sub n is an arithmetic sequence that has first term a sub 1 and a common difference d, the sum s sub n of the first n terms of that sequence is found by, and there's two different formulas here. So s sub n can either be found by doing n divided by 2 times the quantity is 2 times a sub 1 plus n minus 1 times d, or we can find it by doing n divided by 2 times a sub 1 plus a sub n. All right, so there's a lot of different things going on here. So for this version of the formula right here, this is relying on knowing the first term and we know our common difference d. And obviously we know how far out into the sequence we want to go. So what's that nth term? All right, so that's what this version will rely on. This one over here will rely on knowing the first term, a sub 1, and the last term I want to go through, which is a sub n. So I use just a slightly different formula depending on maybe which one is easier to work with, depending on the information that you're given. Now these aren't two totally different formulas, right? All that's going on here is that we're just using the expression for a sub n, which is what we were just talking about. It's that a sub 1 and then plus n minus 1 times d. Right, so this is just relying on a sub n being another a sub 1, that's where the 2 comes in, plus, and then there's your n minus 1 times d. Right, so that's all that's going on between these two versions. So honestly, if you just remember this one where the a sub n, which you'll need to remember it, is equal to a sub 1 plus n minus 1 times d, do we really need to remember both versions of these formulas? No, we don't, right? If you, for instance, remember this one, you can get back to the other one. And I'm going to give you a little story to help you remember this one. All right, this is a very famous story in math about a very famous mathematician, and his name was Gauss. Right, Gauss lived a long time ago. We're talking like 1800s. But this is a famous story about Gauss as a young boy. He was already he was one of the greatest mathematicians, perhaps of all time, because of just how many areas he contributed to. And he just had a way of thinking about things that was a little bit different than how maybe other people understood them. And because of that, he was able to see all sorts of cool connections. So how the story goes is Gauss, as a little boy in elementary school, was given the task, his whole class was given the task by a teacher to add up the numbers from 1 to 100. Right, and the teacher was probably thinking it was going to be a couple of minutes before anybody was going to be able to get this sum, so just gave them the problem, very straightforward problem. Just the counting numbers, add them up from 1 to 100. Now Gauss got the answer almost immediately. Right? So pretty much the teacher gave the question, he jotted down a couple things on a piece of paper, and then immediately raised his hand, I've got the answer, and his answer was correct. So teacher was stunned. How did he get the answer so fast? Let's explore how. So this is what he thought of. So here's what he needed to do. So he was doing a series, right, adding up these terms, 1 plus 2 plus 3, all the way out to 100. Now he thought about pairing these numbers. So if he pairs the first number and the last number together, we'd get 101. So I'm going to write in a couple other terms here. So put in 98, 99, out to 100. Okay, here we go. All right, so if I add the first and the last term together, 1 plus 100 is 101. If I add the second and the second to the last term together, 2 plus 99 is 101. If I add the third number in the sequence and then the third from last number, 3 plus 98 is 101. So you can see then there's kind of doing a very interesting pairing of sums. And how many 101s will we get? Okay, so we will get half as many 101s. Oh, that's not how you spell many 101s as there are terms in the sequence. Right? Because we're pairing them up 2 by 2. So he reasoned, okay, so I'm going to have 50 sets, or 50 pairs of 101. And this isn't too difficult to multiply through, so we get 5,050 is our sum. So tying this back to the formula then, what Gauss thought to do is take the first term and then the last term, right? So there's your 1 plus 100, 1 plus 100, right? So that's giving you your 101s basically. And then you're going to, for however many terms are in your sequence, n, you're going to cut it in half because that's going to be how many pairs you get. Okay, so in this case then my value for n was 100 because I was adding up the numbers from 1 through 100. So that's a way then you can remember this general formula. Okay, interesting story about Gauss, where the formula comes from. Let's go ahead and apply it to a couple of examples. So for these next examples, we're going to find the sum of the first n terms of the sequence. And the first sequence I'm going to be given is 1/3 plus 1 plus 5/3 plus ... plus 7. Now looking at that sequence, what kind of stands out to me is, all right, so I know the first term, right, is going to be 1/3. The last term, a sub n, is 7, but this is leading me to wonder, what is n? Okay, apparently this sequence is going to stop at some point, but I'm wondering how many terms are there? All right, I kind of want to use this formula right here that talks about knowing the first term and the last term, but I got to know a value for n. Okay, so here we go. First off, we'll verify that the sequence is arithmetic. So let's go ahead and take the difference of successive terms. So for the first two terms, I'll get the difference as being 1 minus 1/3. So 1 is the same thing as 3/3. So 3/3 minus 1/3 is 2/3. And just looking at, I only have one more pair that I could have subtracted. If I had subtracted the next two terms, 5/3 minus 1, which would be 5/3 minus 3/3, I also get 2/3, right? So I only have two pairs here, but we can assume that if the difference from the first to the second is 2/3, and the difference from the second to the third is also 2/3, that pattern is probably going to be continuing. So this is going to be an arithmetic sequence. So given that information then, I'm going to be able to use my general formula, a sub n is equal to a1 plus n minus 1 times d. Now we have a lot of formulas floating around. I would strongly encourage you to always start your work with the formula before you start substituting numbers in. It helps commit those formulas to memory. So let's look at that last term. So I know that 7 is going to be equal to a1, my first term, which is 1/3, plus n minus 1. Now I don't know what the value for n is. That's what I'm trying to find. But now I know my common difference is 2/3. So the only unknown in this equation is n. I can solve for it. I'm going to go ahead and distribute that through. So I'll get 7 is equal to 1/3 plus 2/3 n minus 2/3. And then I'll get 7 is equal to, let's put our like terms together. So 1/3 minus 2/3 is negative 1/3 plus 2/3 n. Now this isn't too terrible, but I just want to clear these fractions. I'm starting to get a little tired of working with the fractions. So I'm just going to multiply through everybody by 3 to clear those fractions. So I'll get 21 is equal to negative 1 plus 2n. All right, that looks so much better to work with. So adding 1 to both sides, we get 22 is equal to 2n, or n is equal to 11. All right, cool. That's going to help me. I now know that 7 is the 11th term in my sequence. We will use that to find our sum. All right, so s sub n, which in this case, now I know what my value for n is. It would be s sub 11. Actually, we'll start by recording the general formula. All right, so general formula, s sub n is equal to, and I'm going to use this version over here, n divided by 2 times a sub 1 plus a sub n. Now I know I'm going to go through the 11th term, so it'll be 11 over 2 times my first term, which is 1/3, plus my last term, which is 7. Perhaps cleaning up inside here, 1/3 plus 7, well 7 is 21/3, so 1/3 plus 21/3 is 22/3. And I'm just seeing I can do a little bit of simplifying along this diagonal. So we'll multiply what's left. So 11 times 11 is 121, and then 1 times 3 is 3. And let's just go ahead and leave it like that. You do not need to convert this to its mixed form, and absolutely not, under any circumstance, convert that to a decimal. We're just going to leave it exact. The sum of that sequence is 121 over 3. All right, so let's take a look at our next sequence. So this one, we weren't given the terms, we were given an explicit formula. So for the next sequence, it's going to be formed by doing 4n plus 2, and we're going to find the sum of the first n terms. Okay, so for this one, I don't know exactly how far they wanted me to go out into the sequence to find that sum, so our answer is going to involve the variable n. It might help for us to wrap our head around what some of the terms look like. So if I'm looking at the first term, so n equals 1, a sub 1 is equal to 4 times 1 plus 2, which would be 4 plus 2 or 6. If you wanted to find some other terms, a sub 2 is equal to 4 times 2 plus 2, which would be 8 plus 2, which is 10. All right, so the sequence that is being generated here is 6, 10. Now my common difference is going to be 4, right? What this number is right here in front. So the next term would be 14, 18, so on and so forth. And then the last term that I want to go through is 4n plus 2. If I put commas in between these, that would generate the sequence. But because I want to try to find the sum of all of these, I'm going to put a plus sign between all of them to show that I want to add these up, right? So this would then be my series that I'm trying to add up. Okay, so enough of that. This is trying to wrap our head around what we were given and what we're actually trying to find right here. So I want you to find what you get if you sum all of this up. So the sum, and in general, just with the variable n, would be n divided by 2 times. Now, if I look at here, I know what my first term is, and I know what the last term looks like. So I'm going to use that version of the formula. So n divided by 2 times a sub 1 plus a sub n. So that would be n divided by 2 times, let's see, this is going to be 6 plus 4n plus 2. Cleaning up the inside, we would get 4n plus 8. Okay, and then just distributing this through, we would get 2n squared plus, on the second distribution, looks like 4n. Right, so this would then be my expression for the sum of the first n terms. Now, they didn't ask me this, but suppose, as opposed to having the first n terms, let's say that they tell you to find the sum of the first, we'll say 50 terms. Okay, so then using this, s sub 50 would then be, I'm just going to draw in a little mark right here to kind of separate that from the work that we did previously. Okay, so s sub 50 would be 2 times 50 squared plus 4 times 50. And you can pop that into your calculator and get the sum is going to be 5,200. So if I'm given a specific value for n, I'm going to be able to get a very specific sum because I know exactly how far out in the sequence I'm going to go, and I can have then explicit terms that I'm adding up. But if they don't give you a value for n, if they don't tell you how far out to go in the sequence, then your final answer will also involve the variable n. And then you can use that expression to find the sum if they specify that ending value. So that's finding sums of arithmetic sequences using the formula. The last example is going to be looking at an application. The corner section of a stadium has 20 seats in the first row and 40 rows in all. Each successive row contains 2 additional seats. How many seats are in this section? So just to maybe wrapping our head around what's going on, all right, so here would be, for instance, like the stadium field, all right, and then they have seats all around. These corner sections are usually kind of like a trapezoidal shape, right? They expand out as they get further and further back. And what's going on in this corner section is that there's 20 seats in the first row. Okay, so if I, for instance, look at the first row right here, I would have 20 seats. They also tell me that there's 40 rows in all. And each successive row contains 2 additional seats. So this next row right here would have 2 additional seats or 22 seats. The next row after that gets 2 additional seats or 24 seats, and so on and so forth all the way back through this section. So that 2 additional seats, that's going to be our common difference D. Right? It's going to be how much it's changing from one to the next. And we can also see right here that the 20 seats in the first row, that's going to tell me what my a sub 1 is, or the starting point in my sequence. Now if I look at what information I'm given, I'm going to be summing through 40 terms where my first term is 20. Each term after that goes up by 2. But on this one, I don't know what the last term is. I don't know right now how many seats are in that last row. And I don't have right now any sort of expression that can help me get that. Meaning that explicit formula wasn't given to me like it was like on this previous problem, right? Where they talked to me about what that general nth term was. So there's a couple different ways that you could answer this question. One is if you want to find this sum, you can use the version of my sum formula that just needs for us, so let's go back up here before I write this. If we go back up to these possible sum formulas, if I don't know what the last term is, I could instead use this version where if I know the first term and I know the common difference and I know how far I'm going out, I could just use that. Okay. So let me just write down that general formula. S sub n is equal to n divided by 2 times 2 times a sub 1 plus n minus 1 times d. So for this problem then, s sub 40 would equal 40 divided by 2 times 2 times, my a sub 1 is 20, the first term in the sequence, plus 40 minus 1 times my common difference, which is 2. Okay, so just showing you maybe a scenario where you would want to use that alternate version of your sum formula. All right, so there's a lot going on here. Let's clean this up. So 40 divided by 2 is 20. Inside the parentheses, 2 times 20 is 40, plus 40 minus 1 is 39, so I'd have 39 times 2. So this is going to be 20 times 40 plus, let's see, 39 times 2 is 78. So this would be 20 times 118, which gives me 2,360 seats total. Okay, so that is one way that you could set up and solve this question. Perhaps another way, just to make some connections to come full circle before we close out this section, is we know how to find the last term, knowing that we're looking at an arithmetic sequence, right? So the last term, maybe I'll write that over here, a sub n is equal to a1 plus n minus 1 times d, right? That's in general. Now I know I'm going out 40 rows or 40 terms in my sequence. And I know the first term is 20, and I know my common difference, which is 2. So I could go ahead and clean this up, and I could then figure out then that in that 40th row, I will have 98 seats. Once I have that, we can use then the version of our sum formula that we have been using in the previous examples, the n divided by 2 times a1 plus an, which would be then 40 divided by 2. My first term is 20, and now I know that the last term in my sequence is 98. So I'll leave it up to you to verify that you get the exact same sum this way. This is just a different way to connect all the ideas in all the different formulas that we've seen in order to find the sum that we want. Okay, so to sum up what we've talked about in this section, we have looked at a very specific type of sequence that is called an arithmetic sequence. One of the things that we've done is we've been able to verify whether or not a sequence is arithmetic. Specifically, you're going to be looking for that common difference d, identifying it's there. That's the key feature of an arithmetic sequence. And you find it by subtracting successive terms. One term minus its previous term. If that subtraction always gets you the same number, the sequence is considered to be arithmetic. We then found a formula for a general nth term of the sequence, right? That's this formula right here. So if you tell me how far out you want me to go in the sequence, I then can tell you then what that term is. And then the last thing we talked about is how to find the sums of an arithmetic sequence, either out to a specific term in the sequence, or we came up with expressions for generally what that sum would look like in terms of the nth term. After you practice and master the arithmetic sequences, then we move on to the geometric sequences.